Okay, so last week I gave a brief description of the, I guess like what each board in the BMS system does. But this week I'll be talking more about like how each board does it and some of the decisions that we made while designing these boards. So first of all, I was just going to go over a quick review of capacitors and inductors, just because that will be relevant later on. But essentially, like capacitors, when you have a low frequency or DC signal, it acts like an open circuit. And then high frequency, as you increase the frequency, the impedance increases. And so it starts to behave more like a short circuit when you get to extremely high frequencies. And the current that's drawn from a capacitor is proportional to the rate of change of the voltage. This basis means that the voltage, it resists a change of voltage, but you can draw current from it very quickly and abruptly. Inductors are the opposite, where at low frequencies, it acts like a short circuit. And then as you increase the frequency, the impedance increases and it acts like an open circuit. The voltage can change proportionally to the rate of change of the current. The voltage can change very quickly across an inductor, but the current will always be continuous. Also, capacitors store energy in the electric field, whereas inductors store it in a magnetic field. So this is just a diagram showing the battery box layout that we're currently planning on using. So in the center here, this is the BMS carrier board. These three boards that are vertical are the AFEs, and they're connected to the battery modules to measure the voltage and temperatures. This is the top of the battery stack. So here there's a fuse which is connected to the current sense board, which connects to the high voltage relays. There's one on the high side and low side of the battery pack. And these are the relays that the BMS carrier controls to turn the pack on and off. Then there's fans at the back to provide cooling, which are also controlled by the BMS carrier. And we also have the aux battery here as well. And then there's a whole bunch of low voltage connections to connect to the rest of the car. So first I was going to talk about the BMS carrier. I think it's kind of the most interesting one because there's more that it does compared to the other boards. So for this, I'm just going to go to the schematics in Altium 365. So yeah, it has a controller board on it for most of the processing, but there's also a Raspberry Pi connection as well. So if we want to do more advanced state of charge modeling, that can be done through the Raspberry Pi. And the Raspberry Pi requires 5 volts, so there's a 5 volt converter here as well to power the Raspberry Pi. I'm going to skip the connectors because it's not too important. But yeah, one of the main features of the battery management system is that it communicates through ISO-SPI instead of SPI. So ISO-SPI is just a differential signal protocol that you can convert between ISO-SPI and SPI. So a lot of ADCs and other ICs will communicate over SPI, but SPI is not as robust against noise. And cars are typically very noisy. Like the electrical environment is very noisy. So ISO-SPI is good for rejecting a lot of this noise. So these diagrams are just showing, these were measurements made in Midnight Sun 12, and it's showing the CAN communications in the car. So on the left is just only communicating on CAN. And then if we actually turn on radios for communication, then you can see that there's a lot of noise that gets picked up by the wires. So this is where differential communication protocols are really useful, because this noise is introduced on each of the wires in the differential communication protocol the same way. So it's called common mode noise. And so when you have a differential signal, you usually have two complementary signals. So if one's a high signal, the other one's a low signal, and they get subtracted at the receiver. So then the difference between them will be equal to the original signal, basically. But then if you have noise introduced, which is like this red section, then it will be subtracted, and the result will be that like, it'll basically sum to 0 because it's the same on both signals. So that's one way that you can eliminate common mode noise by using the differential signal protocol. And then it's usually not enough to just use that. Like that's not going to protect you, protect like the communications perfectly against common mode noise. So there's other things that you can do as well. So this is just a diagram showing differential mode noise. So here you'd have 2 wires and there's a current path that goes down one of them through your circuit and then back. In this case, it's a power supply, but this could be like this could be just another PCB that's communicating with this PCB. So in common mode noise, what happens is there's current moving the same direction down both these wires, and then it has another return path through ground usually, because a lot of boards share the same common ground. So another method you can use to remove common mode noise is to have what's called a common mode choke. So this is essentially 2 inductors that share a core. And so when you have common mode noise, which is shown by these orange arrows, this is showing the direction of current, then the current moves through these inductors and creates the magnetic field shown by these orange arrows in the middle here. And these arrows, these magnetic fields would add together constructively. And so you'd have a larger magnetic field. So because there's more energy being stored in the magnetic field, the inductance is higher, and because the inductance is higher for common mode noise, the impedance is also higher, and the common mode signal gets attenuated. When you have differential noise or differential signals, that's shown by these blue arrows that go in opposite directions, which results in the blue arrows in here showing the magnetic field. And they're going in opposing directions, so the total magnetic field would be very small, and so the inductance would be also very small, and so the attenuation of your signal will be very low. So that essentially acts as a low pass filter, and it also lets through differential signals. So if I go back to the schematics, we have a transformer to basically isolate the both sides of the BMS carrier and whatever it's communicating with. And this is so that boards with different reference voltages can communicate. So within our battery pack, all of the boards will be referenced to a different voltage. And so by using a transformer to isolate them, signals are converted to magnetic fields and then back to a voltage. And this prevents any electrical connection between the 2 boards, which allows them to communicate without damaging each other. And it's shown here, the transformer also contains a common mode choke. That's this first half on the left here. And so that helps with common mode noise as well. The other important part that I want to highlight is that we have 2 resistors between the communication lines and a capacitor. And this is to provide signal termination. So when you have high-speed signals, you need to terminate them to basically prevent it's basically just to help communicate faster, I guess. So these diagrams are showing the falling edge of a signal on the CAN bus. And so on the left here, you can see that this is a properly terminated CAN bus, and the signals decay exponentially. So this is because in the communication wires, they have capacitance and inductance, which will store energy in the electric and magnetic fields. And so properly terminating the communication lines will help discharge this energy very quickly, and you can have faster switching times, which can lead to faster communication and less errors in communication. The right diagram here shows when one of the terminations is removed, and what happens is that the signals decay more slowly. So this will reduce the speed at which communication can happen. It is very important to have termination though, because if you completely remove all termination, you'll get waveforms like this, where there's lots of reflections and a very slow decay, which will prevent you from communicating effectively. So going back to this diagram, it's a common method of terminating communication lines is to have this resistor here, a termination resistor. And the value needs to be carefully chosen, because if you make it too large or too small, it won't work very well. So to calculate the optimal termination resistor, there's the maximum power transfer theorem, which states that the maximum power that you can transfer between two loads would be when the loads are equal. So in this case, it's showing that there's like a power supply that has a series impedance, and then there's a load. And if you want to maximize the power that's being drawn by the load needs to have the same impedance as the internal impedance of this voltage source. In this case, the maximum power transfer is between the energy stored in the wires and the termination resistor. So the termination resistor needs to have the same impedance as the wires themselves. And for most time, this is about 120 ohms. So going back to the schematics, you can see that there's two 62 ohm resistors in series, which is 120, well, it's 124 ohms, but it's usually better to over terminate the line than under terminate it. So also shown by this diagram here, you can have just one resistor, or you can have this called split termination. And this is just a method to help, again, reduce common mode noise. So if you have current moving the same direction on each of these lines, and there's only one resistor, then there will be no current that flows through the resistor, because there's can you hear me now?
Your voice is cutting in and out, and we can't see the screen.
Okay, sorry, I got disconnected. Hold on, give me a second. Was I always cutting out, or was there a specific part that I should go back to?
You're going to show us the termination resistors on the schematic again, and then I couldn't hear anything after that.
Okay. It's better now though, right?
We still can't see your screen, but yeah, the audio is better.
Mm-hmm. So yeah, for IsoSpy, we have two 62 ohm resistors, which adds up to about 120 ohms. And then there's also this called split termination. So this is just another method of attenuating common mode noise. So if there's current traveling along both these wires, then the voltage drop across this resistor will be close to zero, and it won't do anything. But if you have split termination, then there's basically a small RC filter that acts as a low pass filter, and I guess bypasses high frequency noise to ground. So that's the most, I would say that's the most important parts of ISOSPY that you need to know. So, and then otherwise, the BMS carrier controls the relays of the battery pack. So for this, we have a high side driver, and this is basically just a switch that connects 12 volts to the output, and it's enabled by the controller board. It also reports a lot of faults and can sense the current that's being drawn from it as well. So the output from here will go to the kill switches in the car. We have two, and then if both of those are closed, the signal will travel back to the BMS carrier, and it will power this relay. So this is a small low voltage onboard relay. This is not the main relay of our battery pack. And then it provides 12 volts to the actual high voltage relays. The reason that we're using a relay here is that we used to just have a high side driver, but semiconductor devices have a tendency to fail shorted. So if it were to fail, then we would have no way of, we wouldn't be able to turn it off. So relays are generally safer for that. This circuit just pre-charges the capacitors that power the relays. So first, there's just a 10 ohm resistor that charges the capacitors. So the current is limited by this resistor. And then after a certain period of time, this MOSFET will will provide like a low resistance path to the relays. So it will basically short the 10 ohm resistor, and it'll have the same effect as if the 10 ohm resistor wasn't there. And then this is basically the relay controls. So each relay is controlled by a single low side switch. So again, there's a lot of redundancy in this path so that we can always turn the relays off if we need to. And these are just controlled by the controller board as well. So when you're switching relays, you require, relays work by using a magnetic, like a coil, an electromagnet to close the switch. So here's an animation of a relay switching. The coil is underneath here, and it pulls this piece down. So when this part is like further away from the relay, you need a stronger magnetic field to pull it in, because the magnetic field decreases with distance away from the coil. But then once it's closer, you don't need as strong as a magnetic field to hold it there. And this is proportional to the current. So this means that when you want to close the relay, you need a higher current initially, and then just to hold it closed, you don't need to provide as much current. So if you want to save power and not waste it by having current flow through this coil, you can have relay economizers that reduce the amount of power that's used by the relay coil. So this is an image of the current. This is like a graph showing the current that's drawn from our relays. So they have a built-in economizer, and there's a lot of switching that happens to help reduce the current that's drawn. As well, it also has like a higher current that's used to close the relay, and then it decays to a lower holding current. So typically the current it takes to close the relay is much higher than the current it takes to just hold it shut. And in this case, the datasheet advertises, I think, 3.8 amps. So to provide this high current, we have these large capacitors here. And like I said before, the current you can draw from a capacitor can change very quickly. So you can draw current very suddenly from these capacitors, which helps to close the relays without having to, because otherwise the power would be coming from power distribution, there's a lot of wires and inductance. And then power distribution might also go into a under voltage fault if you draw too much current from it. So we also have in the relays, there's an auxiliary connection that will detect when the relay contacts are closed, and so there's just a simple circuit here to sense that the state of the contactors. This is important if so it's possible for relays to fail if the contacts get welded shut, or sometimes they can just become oxidized and then the relay won't close properly. So this will let you detect that. Here there's just some low pass filtering that happens, and that goes to an input-output expander, which then communicates to the controller board over I2C. And the BMS carrier also controls the fans. So this is very similar to the relay controls, where the fans have capacitors that need to be pre-charged. So the same pre-charging circuit there. Each pair of fans has a low side switch to enable it or disable it. And then there are there will be 3 fan controllers that will provide a PWM signal to control the speed of the fans. And then they also have tachometer inputs to sense the speed of the fans. So each fan will have an output that outputs 2 pulses per revolution of the fan. So by counting or by measuring the period of the pulses, then you can determine how quickly the fan is spinning. And this is just to make sure that the fan doesn't stall or break, and that it's actually working properly. So that's pretty much the entirety of the BMS carrier. Current sense. So current sense does just that. It just measures current. That's pretty much all it does. So the way that we've chosen to measure current is using a shunt resistor, which is just a resistor with a very small value. And by Ohm's law, you can determine the current that's moving through it. So this resistor is placed on the high side of the battery pack, like I showed you before. So the positive terminal will be at 150 volts. And if the current sense amplifier was referenced to the bottom of the battery pack, or like the low voltage ground, then this would destroy the amplifier. And so to avoid that, the isolated ground for the current sense board is referenced to the low side of this resistor, so that'll be close to 150 volts because there's very little voltage drop across this resistor. And then to isolate it from the BMS carrier, there's a 12 volt isolated DC-DC converter. So this will output 12 volts, but it'll be referenced to the isolated ground at the top of the battery pack, versus the low voltage ground that the BMS carrier is referenced to. And then there's an LDO that provides 5 volts to power the low volt, all the sensors and things on the current sense board. So I was going to take a moment quickly to talk about, so this is like a switching regulator. Anyways, it will turn the output on and off very quickly to change the output voltage. And LDOs are basically just a resistor that will change its value to ensure that the output stays at 5 volts. So in this case, the excess power, so if you went from 12 volts to 5 volts, the excess power is dissipated as heat. Whereas in a switching regulator, it usually has inductors to store energy. And so they're much more efficient than LDOs. But because they have high switching frequencies, there's noise that's introduced to the system. So LDOs are typically used to reduce noise. And that's why we have an LDO on this board, is so that our measurements are accurate and there's no noise introduced to the system. So anyways, this is a current sense amplifier. It's basically just a regular op amp, but it has a very precise gain of 100. So the output will be 100 times the input. And that's referenced to a 2.5 volt reference that's generated by the ADC on this board. So what this means is that if the output would be -1 volt, then the output will actually, because it's referenced to a 2.5 volt reference, it will actually output a 1.5 volt signal instead of a -1 volt signal. And similarly, if the output was a 1 volt signal, then it would actually output a 3.5 volt signal because of the reference. And then this is just a buffer to reduce the impact of any resistance that's not any output resistance from here. So then there's an ADC that actually converts the analog voltage measurement to a digital signal that can be communicated back to the BMS carrier through ISO-SPI. And it actually outputs SPI instead. So there's another IC that converts from SPI to ISO-SPI. And again, this is just the exact same setup that's on the BMS carrier. So same termination, same transformer. One thing I want to quickly talk about for current sense is that there's another very common way that current is sensed, and that's using a Hall effect sensor. So the advantage here is that this senses the magnetic field that's present, and it's inherently isolated from the circuit, whereas we need to add transformers and DC-DC converters to actually isolate our current sense board. And yeah, so the Hall effect is basically where you have a conductor and there's a constant current flowing through it. And then if you apply a magnetic field that's perpendicular to the current, then all the current carriers will experience a force because of the magnetic field, and they will separate. So if this is a piece of metal, the positive charges don't actually move because the positive charges in metal are just atoms. But if you were using a p-type semiconductor for this, you would have holes that could move that would be mobile. And then the charge carriers will eventually reach a point where the electric field between them prevents them from being pushed any further away. And at this point, there will be a voltage that you can measure across the two terminals of this piece of this conductor. So there's a lot of current sensors that are based on this effect. The reason that we're not using this is because it's generally less accurate than using a shunt resistor, and the measurements can be impacted by magnetic fields that aren't part of the high voltage current path. So any kind of interference that the car would be exposed to will also change the measurements for the current. So the analog front ends, or AFEs for short, I mentioned last week that they just measure the cell voltages and temperatures. So the AFEs are powered from the cells that they're measuring, so they don't need to be powered from the BMS carrier, unlike current sense. They still have a switching regulator to step the voltage down to 6 volts, and then in LDO to regulate it to 5 volts. And this is again for noise purposes. So the main part of the AFEs is a battery stack monitor produced by Analog Devices, and it's the LTC6811. So it has inputs for all the cells, and these are basically passed to an ADC to measure the voltage at each one. And it also controls the balancing for each of the cells, which I will talk about later. It also has a couple GPIO pins, which we use. You can configure them to work as a SPI master. So we use SPI to control the multiplexer that selects which thermistor we're reading, and then the thermistor output is buffered and then passed to this GPIO, which has an ADC as well, that measures the voltage and that is converted to a temperature. The LTC6811 has ISOSPI built in, so it communicates directly in ISOSPI. It has the option to communicate over SPI as well, but this is usually disabled when we're actually using these in the car. And then it also provides several, so the VBAT is just the input voltage for to power the LTC6811. And then it provides a couple references, and it can drive the enable signal for the switching regulator. The references need to be buffered because you can't draw a lot of current from the LTC6811. So if you buffer it, you can draw current from the 5-volt rail through the op amp instead of from the 6811. So the cell inputs are fairly straightforward. There are voltage taps that are connected to the cells that are then fused on another board. There's a small connector board on each of the battery modules. And then that is passed to a low pass RC filter here. And then there are diodes to protect for overvoltage cases. So these are Zener diodes. So when 5.6 volts is exceeded, then it will act like a short circuit across the cell. And so this will just prevent the LTC6811 from being damaged by any high voltage transients that might be present on the cell inputs. Communication, again, there's just transformers to isolate the ISOSPI communications from each side. Because there's 3 AFEs, we need to be able to communicate to all of them. So they provide the option of being addressable, or you can also connect them in a daisy chain. So that's what we've done. So the master, so the BMS carrier goes to the first AFE, and then it passes the messages along to the next AFE. And we can communicate that way to each individual one. So cell balancing is important because some of your cells will have lower capacity just by variations in the manufacturing process. And this causes them to be discharged sooner than the other cells. And as soon as they're discharged, you need to stop discharging energy from the pack because you're at risk of damaging these cells and reducing their lifetime and also potentially leading to dangerous situations. But most of the other cells will still have energy in them that cannot be used. And similarly for charging, the lower capacity cells will be charged first, and then none of the other cells will actually get charged fully, which again reduces the capacity of your pack. So balancing is just any technique that keeps the state of charge equal amongst all the cells. There's 2 types, which is active and passive balancing. Passive balancing refers to just discharging the cells that are higher in state of charge, so that when you're charging, like you would discharge these cells and then the pack all the cells could be fully charged. There's also active balancing, which involves moving charge from one cell to another. So in this case, where most of the cells have a little bit of charge left, but these ones don't, you could move charge from all of these cells and charge these cells. And the same is true for this case as well. You could discharge these cells to charge the rest of these cells. And so both these techniques can be used to keep the state of charge somewhat equal. So we are using passive balancing at the moment. This is mainly due to the simplicity and reliability of it. And also it's much cheaper than active balancing. So there's balance control signals that will come from the LTC6811, and they will activate these MOSFETs, which will cause the battery cells to be shorted across these resistors. So these resistors will dissipate all the excess energy as heat. The balancing inputs are the exact same as the cell inputs, but they've been separated so that it doesn't introduce measurement errors when we're measuring the voltage of the cells. And then each AFD has 32 thermistor inputs. So these are used for measuring the temperature of the cells. And then also there's 2 onboard thermistors that are used to measure the temperature of the balancing resistors to make sure they're not getting too hot. Because there are not 32 GPIOs on the LTC 6811, they need to be multiplexed. So this a multiplexer basically is just takes a lot of inputs or outputs and switches them to one input or output. So in this case, we have a lot of inputs, like 32 inputs, and they can be controlled through SPI to select one of them and pass it to the output. And then the output is again buffered to reduce the impacts of basically to help match the output and input impedances to the LTC 6811. And then the LTC 6811, like I mentioned before, has a GPIO that will receive the signal and then pass it to an ADC, which will measure the voltage, and that can be communicated back through ISOSPI to the BMS carrier. And that's pretty much the entire battery management system. Are there any questions?